Right. So this is 3, 2. We're going to use what you learned yesterday, today, as well as what we learned in chapter 2. Yay! Because we always build an algebra 2. All right. Does anybody remember what we learned in 2-1? First part of chapter 2. Properties of exponents. Notice this title is very similar. It's not just properties of exponents, it's properties of rational exponents. But guess what? They're the same. It's the same 7 properties. Do you remember those 7 properties? Things like if you're multiplying with the same base.
Oh yeah, no, I have those in my...
You add, yeah, right? You add the exponents. If you raise a power to a power, you multiply. Shh, you'll see.
You ready?
If you divide, nice, then you subtract.
Excuse me, sir, your head's in the way.
If you are multiplying or dividing in the parentheses, then we can distribute that exponent. And so a lot of you are going, why are we writing this again? I'm not writing this again. I just wrote this, and that's fine. What is the difference in the exponents that we did before and rational exponents? They're fractions. So that means you have to add, multiply, subtract fractions, right? Yay! So let's practice a few and see what happens. I'll give y'all a second to copy that now. Go. Let's look at a few examples and see if you really do got it.
I want to be a
Simplify.
So, 7 squared?
Woo!
7
Oh, God.
7 1/8.
Ooh, I didn't see this.
7 to the 1/4 times 7 to the 1/2.
I'm 1/8. That's 1/8. 7 squared.
7. Yep.
That actually would be 7 and 3/4.
Okay, so let's use our calculator.
You know what? That's actually 49 and...
So we all agree that we should add them. Remember, when you add in your calculator, put the fractions in parentheses. Although I did think we could add, somebody said the right answer. I think Joseph said it. But
No, I said it.
math, enter will put you back as a fraction, which is what you want. Okay, so 3/4. So it's, remember the base stays the same. Don't multiply that base together. You can't combine the exponents and the bases, just one or the other, right? Yep. If the exponents are the same, combine the base. If the bases are the same, combine the exponents. So this gives me 7 to the 3/4. How about another?
Why don't you want us writing it out as like 4.3?
Because I want exact answers.
Wait, see exactly.
You just say if the exponents are the same, combine the base.
Yep.
So if it were the same problem, what it would be 8 1/4 times 6 1/4.
The 8 times 6, but keep the 1/4 the same. It's kind of the backwards of that property. It's actually the one I'm doing right here. Okay, so here, see how the exponents are the same, but the bases are not? You can't combine both, so you pick which one. So here, because the exponents are the same, I can multiply these bases. It's the backwards of, come on,
Like the 7.
this property. Where it tells you can distribute it in if you're multiplying, you're kind of undistributing it there, so that I could get 12 to the 5th to the negative 1/5. Okay. Wake up! So yes, you would multiply those together to get -1, which then of course flips over this way.
I like to get out of her, though.
Wait.
Make me feel
I thought you would add the 5.
Why did you make that 5 roll?
I
I bet you would add the 5.
You can only add the 5s if the bases are the same. The bases are not the same. So you might want, okay, you might want to write this note. When multiplying or dividing, this is the only time it works is when you multiply or divide. If the bases are the same, if the bases are the same, combine the exponents. But if the exponents are the same, combine the bases. Never both. Never both. If you get a problem and they happen to both be the same. In other words, what if I got something like, pick one. 5 to the second times, you need me to go back? Okay, but don't do both. Like you can't do, if you had 4 to the 5th, 4 to the 5th, you couldn't do 16 to the 10th. You'd have to pick one and stick with it. So here, 5 to the second and 5 to the second. I can choose, since everything's exactly the same and I'm multiplying, I can either do the bases or the exponents, but not both. So I could do 25 squared or 5 to the 4th, and guess what? Both of those values are the same.
Now what happens if you were dividing it?
Same deal.
Could you do it?
Well, but anything divided by itself is 1.
So it would just be, yeah, that's what I'm saying.
So 5 squared over 5 squared would just be 1.
Dude, wait, I don't understand. Oh, wait, they're the same thing.
Do this one. Oh, no, sir. Not on my board. Simplify. Simplify.
Wait,
Wow, y'all go dark fast, don't you? Huh? So, I don't know what it comes out as.
It's 1.
1.5, which is
Wait, no,
1/4, which is
5/4. It's 5. See, you guys are confusing me. I have 5.
all right. Let's kick it up a notch.
Sweet keep the thing.
how's your bird? That's why I helped you back.
You didn't make it back? I'm scared.
Algebra.
Algebra.
That's so funny. That's 2 over 5. There it is.
Yes.
Great observation.
There it goes.
All right, so take a look. Take a look at this one.
That's 0.
What? You're right, though, Wills. Everybody's laughing, but you're right. What's 0?
The top, the numerator.
That?
Yeah. and then that's 1.
That's right.
And then you flip it. And then.
You're done.
Yeah. Sweet.
All right. So exponents are not that bad. But then,
Oh my gosh,
and then we use the radicals for some similar properties because radicals are really exponents written a different way, right? They're actually rational exponents. They're just written a little bit differently. I feel like y'all are off in like another world over here on this side. Like it's just slid so much. I wasn't talking to you, Wills. I was talking to the girls there because these desks keep sliding this way. All right, so just as a reminder, when we have radicals, we have 2 properties that we have used backwards and forwards. And that is, if I am multiplying or dividing, I can split those radicals up, right? Okay, so we're going to use some of those techniques to simplify radicals with different roots other than the 2. All right, interesting, I know, it's exciting. Contain yourself. Hold back, I know it's hard. What if I had the 5th root of 96 divided by the 5th root of 3?
Who's that?
You would just put them under the same radical, right? Which is the 5th root of 32?
Oh my. Which is 2.
See, look at y'all knowing that. Just for the slow.
Okay, so my question
Not this time, why?
Oh, well. Oh.
It's an odd root.
Well,
It's an
no, I
odd root.
thought that the number being rooted
Yeah, that was
was
confusing.
probably.
Okay, so
Alright.
Yeah. All right.
what's the bottom number?
Don't change the 6.
Don't change it, Miss McGee.
Square root of 6.
I changed it through 32.
So, guys, shh, shh, shh. Let me reel you back in. Shh, shh. Say that one more time.
So what if the top number stays top and the bottom like the same one?
You could not combine them because they have to be the same radical. Just like the exponents have to be the same, the radicals must be the same. That's a great question, though. Which kind of leads into the next one. I'm not going to spend much longer on this because that kind of leads into the addition and subtraction that I want to talk about for just a second. Let's say that I had the 4th root of 10 plus 7 times the 4th root of 10. Okay? Before I can combine these, all right, they have to be, you have to think about them as almost like a variable expression, okay? The only way you can add radicals together is if they are like radicals. Would it be what? Yes, it absolutely would. Because if you think about the 4th root of 10 being like your x, so if I had x plus 7x, what would I get? 8x. So it's 8, 4th root of 10. So like radicals just means that they have the same root and the same, what do you call this number under it? The radicand?
I always thought the line was around.
The line?
What's the line? So this little,
It's just, yeah. It's just the,
It's a squiggly dick.
yeah, it's the house.
How erratic.
All right, so that's the only way you can combine them, and you treat them just like. Now, the question is, what if I get a radical that's not, if I get these 2 radicals and they're not like radicals, for example. Here's where we get into the sticky part. If I have the 3rd root of 5 plus the 3rd root of 40, can I combine those? Nope, they're not. They're definitely not like radicals, right? The root is the same, but what's not the same here? The radicand under there, right? So, does anybody see something I could do? Simplify. Remember how we simplified the square roots? We took out a perfect square. Well, since this is no longer square roots but cube roots, I can see if I can split it up with a perfect cube. So,
5 and 8.
good job. Which one of those 2 is the cube?
8.
The 8.
Guys, be nice to him.
Do we agree that that is the same thing? Remember that property? I can split them up. Cubed root of 8 is 2. So now I have the cubed root of 5 plus 2 times the cubed root of 5. Oh, surprise.
3 root of the 3.
Spit it out.
I knew what you were trying to say. OMG, tell me what you think.
You know, it's just gonna take a while.
There's nothing new. There are no new concepts here.
Everything.
It's just kind of,
You're adding more.
yes.
I want to see the other one.
You're like you're adding a record.
Let's see, I've got 2 examples. If you can get through these 2 on your own, I feel good about being done. So let's see what happens. One of them will be radicals and one of them will be exponents.
Just give me a second.
All right, let's talk about it. The numbers in front, yes, divide them by 3, so I'm left with the 2 up top.
And x to the 1.
X to the,
Wait, how did you? Over 1.
Because you're subtracting. You're subtracting together.
That explains.
We're taking the least one times later. She's the teacher.
It's just like terms, dog.
Isn't that it?
3/4, that's it.
Got the answer? Yes.
Then why'd you do one?
Yeah.
I didn't work it ahead of time.
Oh. Oh.
That's the answer. I didn't know there wasn't going to be a denominator until we worked it together. All right, last one.
It's good stuff. Dude, don't start that.
Okay, stay with me as I walk you through this one.
Okay, so first.
All right, we know the square root of 9 is 3. Now, I want you to think about something with me for just a minute. If I have the square root of w to the 5th, and I am trying to simplify and break down, right? Would you agree that this is the same thing as the square root of w squared times the square root of w squared times the square root of w?
Yes.
I'm breaking them down by 2 since that's the root on the outside. Because now this is 3 times w times w times the square root of w. What's the square root of w squared? Okay, so this is 3w squared times the square root of w. Do you agree with that?
Why do I agree? I get it, but why do we have to? So then can you do the same?
Because you have to because you can't combine them the way they are. The roots may be the same, but the radicals are not.
Wait.
So I have to try to simplify them if I can.
Say W.
W. It's a W. If you write two U's.
W is the only letter in the alphabet.
This stuff is dumb hard. Like, I'm really trying to process it. You can't spell Z.
J.
Okay.
J.
Now let's do this one. All right, let's do this one, guys. I'm going to do W squared and then W. Because I'm looking, remember, I'm looking for perfect squares to take out. Just like if it was a third root, I'm looking for perfect cubes. Here, I'm looking for perfect squares, so I can take one out. So I'm left with W times the square root of W.
Okay.
Which is
This is pretty cool.
W squared times the square root of W. So now my equation is, 3W squared times the square root of W minus W squared times the square root of W. You're right, Jeremy, say it. Yes. Y'all are awesome.